In this section, we will discuss exponential modeling. That is, how do we use exponential functions to model real-world situations? I've come across some of these formulas before. For example, this must look familiar. And this particular formula is very similar to the compound interest formula that we've done. So Q, let's say, is the notation for the new value. So we are assuming that something changes by a certain quantity changes by a certain percent every year, constant percent. So we know it's an exponential function. And Q naught is the initial value of that quantity, which either increases or decreases, which is grows or decays. The rate of growth is important. It's given in the form of a percent or a fraction. And T is the time at which we're interested in knowing what the quantity is, whether it's grown to a certain quantity Q or decayed to a certain quantity Q, starting with the initial quantity Q naught. So this is an important formula. Should remind you of the compound interest formula that we've come across before. What makes this an exponential function is that the variable T, which is time, that is the independent variable on which the final quantity depends, is the variable. So the independent variable is the exponent. So that makes it an exponential function. So if you have y equals 2 to the x, for example, notice that x is the independent variable, y is the dependent variable, y depends on x. X is in the exponent's place, and that's what makes it an exponential function. Now, these two we've come across before. A certain quantity doubles in a certain period of time. T double is the time it takes for a certain quantity to double. So if, let's say, T double is equal to 2 years, we start off with 10. In 2 years, it's going to be 20. In another 2 years, it's going to be 20 times 2, which is equal to 40. So it doubles every 2 years. And then the next doubling happens in 8 years. So it becomes 4 times 2, that is 80. The double of 80 is 160. So this is in 2 years, it's 10. Initially it starts off with 10. In 2 years, it's 20. In 4 years, it's 40. In 6 years, it's 80. And in 10 years, it is 160. So the quantity doubles every 2 years. Now, similarly, if T half is equal to 2 years, so at the beginning, your Q naught, let's say, is 1. The quantity in 2 years is going to be half of that. If we start off with 1 gram of some radioactive substance, and let's say which has a half-life of 2 years, then in 2 years it becomes half a gram. In 4 years, it becomes half of half, which is half times half, that's 1/4. 1/4 is half of half grams. And you can kind of see the pattern. And half of 1/4 is 1/8. So in the next 2 years, that is Q6, it becomes 1/8. Q8 in 8 years, it becomes 1/16. So the quantity keeps decreasing to half of itself every 2 years. So that is the difference between half-life and doubling time. Let's look at the first problem. So we have the price of gold decreases. So it's a decrease, it's a decay at a monthly rate of 1%. And that is the rate at which it's decreasing, it's 1%. By what percent does it decrease in 1 year? We need to figure out the percentage by which it decreases in 1 year. So what is it that we know? 1 year equals 12 months. And why do we change it to months? Because it's a monthly decrease of 1%. So we need to figure out in steps of 1 month. The rate is negative 1% because it's a decrease, and that's negative. It's negative 0.01. So Q equals Q naught times 1 minus 0.1 to the 12th power. So when we simplify it, we get Q equals Q naught times 0.99 to the 12th power. So Q, the quantity after 12 months, is 0.8864 times Q naught. That is the same as saying the quantity that remains after 12 months is 0.8864 of Q naught. It makes more sense when we change the 0.8864 to a percent, and now it's really clear. Q, the final quantity after 12 months, is 88.64% of the initial quantity Q naught. So what is the decrease, the percentage decrease in 1 year or 12 months? We started off with a whole, which is 100%, minus what's left is 88.64%. So there has been a decrease of 11.36% in 12 months. Here's an interesting example. Wars sometimes drive prices up, and that's called inflation. And in Bosnia during the war, the inflation rate was extremely high, 90% per month. At this rate, by what percent would the prices increase in 1 year? Since the rate is given on a monthly basis, this is per month, we need to figure out what the prices were. By what percent did the prices rise in 12 months? So the percent by which the prices change or changed is positive 90%. So that would be an increase of 90%. That's positive 0.90. So if Q is the price after 1 year, which is equal to 12 months, so Q is the price, the letter that we use to denote price after 1 year. Q naught is always the initial price. So Q equals Q naught times 1 plus R to the 12 months, which is T, the variable. Q is equal to Q naught times 1 plus 0.90 to the 12th power. Simplifying, we get 1.90 to the 12th power is 2213.31 times Q naught. So if a certain object cost $1, although their currency is not in dollars, just to get an idea, then the price after 12 months was $2,213.31. That's how high it was. So changing it to a percent by multiplying this quantity by 100, just like we did in the previous problem, we get the final price after 12 months was 221,331% of the initial price. Similarly, if we had to figure out the price in 1/30th of a month, we plug in all the numbers just the way it is with the time equals 1/30th of a month, which is really 1 day. We need to keep the units consistent. Since the rate is given as a percentage per month, we need to change all time, any sort of time unit to a month. So 1 day would be 1/30th of a month. So this is equal to 1.90 to the 1/30th of Q naught, which is equal to 1.0216 Q naught. Changing it to a percent, it would be 102% of Q naught. So the price in change in one day is 102% of what it was on the previous day. So that is the rate at which the prices were increasing. So the annual world oil production was 518 million tons in 1950. Production of oil increased at a rate of 7% per year. So the units here for time are years between 1950 and 1972. But the rate of growth then slowed, and the world oil production reached approximately 3.9 billion tons per year in 2008. What was the world oil production in 1972? So we're looking at a time period from 1950 to 1972. So as time increases, the world oil production increases at the rate of 7% per year. The minute the increase is by a percent, you know it's an exponential function, and you would need to apply Q equals Q naught times 1 plus R to the T. You'd have to apply the exponential function. So the rate of increase is positive 0.07. It's an increase, so it's positive. Q naught is the oil production at the beginning of time, which is in 1950. We need to figure out the oil production in 22 years, that is in 1972. So 1972 minus 1950 is equal to 22. So using the exponential equation, plugging in the initial value of 518 million tons times 1 plus R, R is the rate, 0.07 to the time, which is 22, we have 2,294.95 million tons. So since the production of oil in 2008 is given in terms of billions of tons, let's compare it to that quantity, and it's easy to compare it only if we change the units from millions to billions. 1 million is 1 followed by 6 zeros. 1 billion is 1 followed by 9 zeros. So we can write a billion by 1 followed by 6 zeros times 1,000, which is the same as saying 1 million times 1,000. So 1 billion is equal to 1,000 million. So using dimensional analysis, since we want to change millions to billions, we multiply by 1 billion over 1,000 million. The millions get cancelled, and we get 2294.95 divided by 1,000, and we want the units to be billions, and that's what we have. So that's about 2.29495 billion tons in 1972.